Good morning to all. I am B. Tejashwani from Srinivasa Ramanujan Institute of Technology. I am from the Department Electrical and Communication Engineering and my roll number is 234G1A04B8. Today my topic for the presentation is calculate K such that f of x comma y equals to x cube plus 3xy square may be harmonic and find its conjugate. And the subject name is probability and complex variable, and the subject code is 23A54302. Introduction to harmonic functions. Harmonic functions are solutions to Laplace equation. A function f of x comma y is harmonic if it satisfies. Understanding these functions is essential in fields like physics and engineering. Harmonic functions. Suppose that f equals to u plus iv is an analytic in neighborhood nu equals to nu of z naught. Moreover, suppose that the partial derivatives of u and v are differentiable and that the second partial derivatives are continuous functions on nu. From Cauchy-Riemann's equations follows. As the second partial derivatives are continuous on u, we have u of zy equals to u of yz and vxy equals to vyx. It follows that u of zz equals to u of yy equals to 0 and vzz plus vyy equals to 0. Definition of function. We consider the function f of x comma y equals to x cube plus 3xy square. The goal to determine the value of k that makes f harmonic. We will also explore the conjugate function associated with f. Conditions for harmonicity. A function is harmonic if its second partial derivatives satisfy Laplace equation. The equation states fraction of partial square of x. We will compute these derivatives for our function. First partial derivatives. The first partial derivative with respect to x, partial derivative is f of x equals to 1 plus 3ky square. The first partial derivative with respect to y is f of y equals to 6kxy. These derivatives are necessary for calculating the second partial derivative. If z equals to f of x comma y, then partial derivative with respect to x is dou f by dou x or f of x equals to limit h tends to 0 f of x plus h comma y minus f of x comma y by h. Partial derivative of f with respect to y, dou f by dou y or f of y equals to limit h tends to 0 f of x comma y plus h minus f of xy by h. Second partial derivatives. The second partial derivative with respect to x is f of xx equals to 0. The second partial derivative with respect to y is f of yy equals to 6kx. We now substitute these derivatives into Laplace equation. Partial derivative of f of x comma y equals to xy by x square plus y square. Applying Laplace equation, substituting into Laplace equation results in 0 plus 6kx equals to 0. For this equality to hold for all x, we must have k equals to 0. Thus, the only value of k that makes f harmonic is k equals to 0. Verifying harmonicity. With k equals to 0, the function simplifies to f of x comma y equals to x. The second derivatives are verified. F of x equals to 0 and f of y equals to 0. Therefore, f of x comma y equals to x is indeed harmonic. Finding the conjugate function. The conjugate function g of x comma y is defined such that f plus ig is analytic. To find z, we use the Cauchy-Riemann equations. F of x equals to g of x and y, f of y equal to minus g of x. With f of x equals to 1 and f of y equals to 0, we get g of y equals to 1 and g of x equals to 0. Solving the conjugate function. Integrating g of y equals to 1 gives g of x comma y equals to y plus cx. Since g of x equals to 0, c of x must be constant. Thus the conjugate function is g of x comma y equal to y plus c. Conclusion. We determined that k equals to 0 for the function f of x comma y to be harmonic. The conjugate function associated with f is g of x comma y equals to y plus c. Understanding these concepts is crucial in complex analysis and applications. This is about my presentation. Thank you.